All right, problem 66 made it all the way to the end of the test. A couple comments. I make these videos because frankly they're fun for me to make, and I really like the idea that maybe they help some people out. I didn't monetize any of these, so you shouldn't be seeing any ads when you watch them, or at least no more than YouTube automatically puts in there. It's just something I do because I enjoy it. I'm going to make some more subject test prep. Not 100% sure what that'll look like at this point, but they'll be fairly similar to these videos. In case you're interested in that, as I start to make them, I'll put them in a playlist, and I'll link that playlist in the descriptions of all the videos in this playlist. Since some people ask, it's totally unnecessary, but if you do want to thank me for these, I suppose you could buy me a beer or something. If you're interested in that, this is my Venmo. The only thing I ask is pick out a specific drink. I can just imagine being out at dinner with the fam, and my phone buzzes, and I look at it, and it's like, well, I wasn't going to have a third margarita, but some dude named John online just bought me one, so I guess someone else is driving home. I don't know, whatever. Definitely no pressure at all. You don't owe me a damn thing. Anyways, on to the problem. So what's going on in this problem is we're starting out with this space x, which is just the set of integers greater than or equal to 2. In case it's easier for you to picture it, here's our set x. And when we talk about a topology on this set, what we're interested in are the open sets in this space. What it tells us here are that open sets are the empty set and arbitrary unions of these things u sub k. A given u sub k is the set of all n in this space so that n divides whatever k is. So for example, if we talk about u sub 2, this would be the set of all integers greater than or equal to 2 that divide the number 2. The only integers that divide the number 2 are 1 and 2, but we're limiting ourselves to integers that are greater than or equal to 2. So u sub 2 would be the set that only contains 2. What about u sub 3? Kind of the same story. That'll be the set that contains 3. But for u sub 4, we finally get a set with more than one element. This set would contain the elements 2 and 4. Why? Because both 2 and 4 divide the number 4. U sub 5 would just contain 5. U sub 6 will contain 2, 3, and 6. You get the point. But remember, these various u's here aren't our only open sets. Open sets are arbitrary unions of these guys. So some examples of open sets. Well, the empty set is 1. U sub 2 would be 1. So the set containing the element 2 is an open set. U sub 8 is 1. The set containing what? 2, 4, and 8, I suppose? The union of u sub 2, u sub 3, and u sub 5. Sure, that would be the set containing the elements 2, 3, and 5. You get the point. Okay, so now that we kind of understand this topology, we can get to the question. What the question asks is for any element in this space, for any integer greater than or equal to 2, what is the closure of the set containing that element? I guess to answer that, you need to be comfortable with this idea of closure. Lots of different ways you can think about closure. The one that I prefer, that'll be the most relevant for this problem, is that the closure of some set S, which is often denoted S with a little bar up on top, is just the smallest closed set that contains S. So in the standard topology on the real numbers, if my set S is the open interval from 0 to 1, the closure of S would be the closed interval from 0 to 1. It's a closed set, and it's the smallest closed set that contains this open interval. What makes this set closed? Well, the fact that it's a closed interval guarantees it'll be a closed set on the reals with the standard topology, but maybe a better definition of what a closed set is it's just the complement of an open set. This definition might not be necessary on a more standard topology, but in these kind of strange topologies like this one that we're just kind of wrapping our head around, I think the easiest way to understand closed sets is to think about them as the complement of open sets, because open sets are explicitly defined here. So for example, we have some examples of open sets. If we want some examples of closed sets, we just have to consider the complement of these open sets. The complement of the empty set would be the entire space, X. The complement of u sub 2 would be all elements except for 2. So 3, 4, 5, and so on. The complement of u sub 8 would be all elements of x other than 2, 4, and 8. And same idea down here. The complement would be all integers greater than or equal to 2 other than 2, 3, and 5. So 4, and then all numbers greater than 6. Okay, so these are some closed sets. When we talk about smallest closed set, smallest is defined in terms of containment. So you might notice that all elements of this set are also in this set. That, let's see, if I call this, I don't know, O1 and I call this O2, then maybe this would make sense to be called C1, and then this I could call C2. C2 is a proper subset of C1, so C2 is smaller than C1. All right, I think we have all the definitions that we need. What the question asks is for any element of this set, so any integer greater than or equal to 2, what is the closure of the set containing only that element? Well, maybe we start with an example. Let's let n equal 2. So then we need to find the closure of the set that only contains the element 2. Well, remember, for the closure, we want the smallest set, and we want it to be a closed set. But the way we think about a closed set is it's the complement of an open set. So the smallest closed set containing 2 would be the complement of the largest open set that doesn't contain 2. Okay, so what's the largest open set that doesn't contain 2? Let's build it. It's the complement of some set. So here's the set, and I'm going to take the complement of this thing, and it's the largest open set not containing 2. So I know not to put 2 in here because it explicitly says it doesn't contain 2, and I'll put everything else in here that I possibly can because I want it to be as large as possible. So I'm definitely going to throw a 3 in there. Should I put a 4 in here? You might be thinking that you should, but don't. Because remember, this is an open set, and the way I build open sets is by taking unions of these guys. And because of the way these U's are constructed, any U that contains a 4 is automatically going to contain a 2. Wait, why? Because U sub k is the set of all integers greater than or equal to 2 that divide some number k. But if 4 divides k, then 2 necessarily divides k. So if 4 is in one of these U's, then 2 is also in that U. So if I have an open set containing 4, that open set also has to contain 2. But I'm told that my open set does not contain 2, therefore it can't contain 4. What about 5? Yeah, absolutely throw 5 in there. What about 6? Maybe you can see where this is going. We don't want to put 6 in here. Why? Because any set containing 6, U sub 6 for example, or U sub 12, or U sub 18, is automatically going to contain a 2. The fact that 2 divides 6 means 2 is going to divide any number that 6 divides. So as I build this set, I can only add in numbers that 2 does not divide. In other words, I can only have odd numbers. The key realization is that if some integer m is in U sub k, then all divisors of m are also in U sub k. What that means is that if some integer m is not in U sub k, then no multiples of m can possibly be in U sub k. Because open sets are just unions of U sub k's, the minute I create an open set without a 2, I'm creating an open set without any multiples of 2. What I'm saying is the closure of this set that only contains 2 is just the complement of this set that does not contain any multiples of 2. What's the complement of this set that doesn't contain any multiples of 2? It's the set that contains all the multiples of 2. Closure of 2 is just all the even numbers, or even integers greater than or equal to 2. Similarly, if we were building the closure of 3, what we'd want to do is take the complement of the largest open set that does not contain 3. It could have 2 in there, sure, but it can't have 3 in there by definition, and therefore can't have any multiples of 3. What's the complement of the set containing all the integers greater than or equal to 2 that does not have any multiples of 3? That's just the set containing all of the multiples of 3. One more just to hammer this home. What would be the closure of the set containing the element 6? Well, it's going to be the complement of some set, specifically the largest open set that does not contain a 6. Can it contain a 2? You might think no, because 6 is a multiple of 2. No, that's backwards. It's totally possible for this to contain a 2. How? Well, just consider U sub 2. This doesn't contain any 6's, so there's no problem with throwing this in the union to create this largest open set not containing a 6. Similarly, I could throw a 3 in there, maybe including this in my union, and a 4, and a 5. Sure, no problem. I certainly can't contain a 6, though, by definition. You can contain a 7, an 8, a 9. All those are fine, but you can't contain a 12. Why? Because how would you get a 12? You would need the k in U sub k to be a multiple of 12. But since 6 is a divisor of 12, any set containing a 12 is automatically going to contain a 6. Since I can't contain a 6, I can't possibly contain a 12. The largest open set, not containing a 6, is the set containing all the elements other than multiples of 6. Therefore, the complement of that set, which would be the smallest closed set containing a 6, would just be the multiples of 6. More generally, the closure of n would just be the set containing all of the multiples of n. It looks like answer B is our answer. Sn represents multiples of n if s is a positive integer. Kind of a fun little problem and a good way to end this test. Hope that's helpful and good luck with your exam.